Well, this is my second take because I told myself I was going to make a quick video and I spent 20 minutes explaining this, which I shouldn't have. It's much simpler than that. So we'll give it a go. We'll try and get it done in an order of magnitude less. We'll see how we go. So what this filter does is it allows us to plot in a color channel against another color channel and to show us how the colors of the image are distributed and what colors we have in the image. So for this image we have quite a wide range of colors, and we're plotting against the U and V axis of the YUV color space, but we can choose other channels and put them on whatever axis we like. So for example, here's luminance of YUV against the V of YUV. We can do hue versus saturation of HSV, and so on, and depending on what the display we have depends on how useful the information will be. We have there's a few different types of plots. We can plot the colors as just dots, which is useful if you want to see all of the colors. You plot them as circles, which means you can see it easier. Circles scaled by luma means that the darker colors have bigger dots and the lighter colors have smaller dots, and that means that lighter colors and darker colors that need to be plotted on the same coordinates, you will be able to see both the colors. For example, in these yellows up here, you can see that we've got some darker colors plotted underneath some of the lighter colors, and we can see them both. Whereas if we just went to circles, then some colors start to get obscured by some of the other colors at the same location. We can also do a heat map, and this renders circles as transparent, and then as the same color gets plotted on the same pixel, then the brightness increases, and so you can see the areas. I'm just going to drop down the number of pixels that we're actually looking at the image here, and we'll change this back to U and V. Right, so and so the brightest areas on the heat map are where there are a lot of pixels of that color, and obviously there's a big lot of white there, and there's a lot of white, so that's the heat map. One of the things is that it's quite slow to render. If you have a 24 megapixel image and you try and render 24 million pixels on a graph, that's not going to be very fast, and probably not going to give you any useful information. So there's a few ways that we can actually limit the number of pixels that we're actually plotting. On everything but heat map, duplicate colors are removed, and if we lower the resolution of the color, then more pixels seem to be the same. So if we go, let's go down to 4 bits, for example, you can see how the plot is got very discrete locations because there's only 4 bits of resolution for the location, and so colors that are close get removed, and so we actually need to plot less colors, so that speeds things up. Plot size is pretty straightforward. The preview here doesn't really show the difference in the plot size, but if you were to apply the filter, then this is the output size. If I go down to really small, you can see the effect there. Let's just set it somewhere. And maximum samples is the maximum number of colors. Once we've removed the duplicates, we can remove even more. So for example, here we're going to plot 16 colors. Now obviously very low numbers aren't very useful because they won't get all of the colours in the image, but as you go up to a very high number, if we did a high number at high bits, then obviously there's a bit of a pause, and if we go into heat map, then that's going to take quite a long time to render, so we try to avoid that. So we can render the plot with just the plot, or we can put some axes behind it to give us a bit more information. So if we're rendering Y against V here, then you can see on the V axis we've got greenness to redness, and on the vertical there's luma, and if we get rid of as many pixels as possible, then you can see that there's a grayscale fade on the vertical axis there. Or we can do an underlay of the entire color space of the axes that we're comparing, and that gives us an idea of the colors that aren't in the image. We can also turn on generating test colors, so we'll need to, let's get this back to something that will work for the test color. So here we go. We can render excuse me, we can render the full range of RGB colors based on the amount of bits and our maximum samples, to give us an idea of the entire color space in the graph. So for example, in YUV, you get this kind of hexagonal shape. Sometimes the amount of samples that you are showing in the test colors, you get some aliasing, so you get some weird effects like we did when we were doing a higher number of colors there, so you just need to shuffle it around if it looks weird. And finally, or nearly finally, you can change how the plot's laid out so it can make more sense in your head. So previously we were plotting, let's plot value. So here, for example, the dark colors are at the top and the light colors are at the bottom. That doesn't make any sense to me, so I can mirror around the y-axis, and now the bright colors are at the top and the dark colors are at the bottom, and we can rotate it, and just so that it makes sense in your head and you don't have to like do a transformation in your head when you're looking at the graph. There's one last thing that I want to show you. I have this image of skin tones. So it's entirely of skin tones, and if we plot U against V, then we can see they all fall within that area, and that gives us some very useful information if we are retouching a portrait or doing some color adjustments on a portrait. We can see if our skin tones are actually falling within the range that we expect for skin tones. Alright, I'm going to stop there. I don't think I was quite as quick as I'd liked, but if I stop now it won't get any worse.